Evening, welcome to Space Oddities. I hope you are all well. Thank you for joining us, and on this Tuesday, as always. And let's hope that we can bring you some more good stuff from the weird and wacky universe that we live in. Hope you've all had a great week. It's lovely to see everybody here again. So this evening, what have we got for you this evening? We have got, first of all, we're going to look at planets today, and we've got a thing called Walking with Planets. And we've also got Lou talking about, I hope, some yardsticks that we can use with planets. If I've got that right, Lou.
That's pretty close.
Yeah. Somebody's got their volume turned up. I'm getting feedback from it. So if we could just somebody turn your volume down so we don't get that. Okay, so we've also got, of course, regular features tonight. We've got the news. We've got Constellation of the Week. We haven't got an Einstein of the Week this week because I haven't seen anything. Yeah, I know. I haven't seen anything worth including this week.
People finally wise up. Is the education level just take a huge leap or something?
I think it did this week. You know, considering how absolutely weird and surreal the last few weeks have been on Einstein of the Week, it's all got a little bit normal this week. So it won't last. Don't worry, it won't last. It can't.
All right.
So there we are. So anyway, joining me this evening, the usual suspects: Michael and Williamina, our resident head of Nebulae. Dave's here, and Roger's here, and of course Lou's here. So thanks, guys, for being here this evening. Just normal housekeeping stuff before we get started. If you would like to support Space Oddities, why not buy us a coffee? And you can scan the QR code here, or click the link that's just appeared in the chat to keep our caffeine levels sustained. And you can also, of course, for this cold, wet weather that everybody's having, except me and Dave. Dave's got a nice. How many degrees is it in California, Dave?
What did I say? 20, 23, 24 C, 70 something.
Yeah. So Dave's nice and warm in California. Here in Spain, it's not quite that warm. It's about 14, 15 degrees C, but it's been glorious blue days we've had recently. We did have some rain last night, just a shower that lasted about 5 minutes, but that was it. Yes, you can buy your Space Oddities hoodies from the Space Oddities shop. They are £40, including UK postage and packing. Very good for this type of cold weather. And if you're outside the UK, please add £10 to the total value of your order. Of course, it's about time you started thinking about T-shirts for the summer as well. So we offer you the Space Oddities T-shirts for £20, including UK postage and packing. And again, you can scan the QR code or click the link that's appeared in the chat. If you would like to make a donation directly to Space Oddities, please click the super chat icon. That's the one with the $sign underneath the chat window, and that will allow you to make a donation directly. And as I always say, because I have to say it, every bit of money that we receive from you goes towards keeping Space Oddities going. So we're very, very grateful for your contributions. And long may they last. Okay, let's just just want to have a quick look in the chat, see who's in. Heidi's here. Hi, Heidi. Derek's there. Stuart's there. Hi, Stuart. Oh, Gerard, thank you very much for your donation, sir. It's very kind of you. Very kind indeed. Sandra's here. Mike Beer's here. And somebody called Michael Bryce is here as well. No idea who. So chuck him out, somebody. And
Interloper.
And a few others. So you're all very welcome. Okay, let's kick the ball rolling. So let's move over to the news for this week. Not many things in the news for this week, but nonetheless a few really good. Hang on, what's gone horribly wrong here? Just give me one moment, please. This won't take a second.
Dooby 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 doo.
Yeah, I know.
Doo doo.
Yeah, the irritating supermarket on. The supermarket music. Okay, right, that should have fixed it. Yeah, here we are. Right, okay. So here's the news for this week, 10th of February. So let's have a look and see what we've got. Just 4 stories today. The first story, you may have seen the video that we published on this a couple of days ago, because we wanted to break the news as quickly as we could. because the UK government is proposing cutting 30% of the research budget for astronomy and physics, which is, as it says in this article from MSN.com, pretty disastrous. Why they're doing this? Well, they've said that they want to put the money into things that are of use to the general public, and the two things they quoted were life sciences, which, you know, I don't think anybody can argue with putting money into life sciences.
Well, no, they're not real science, but yeah, okay.
Exactly. You know, there's not much science in it. You know, you're either dead or alive. I don't see why.
I know, right?
Yeah. So, but the other thing that the government quoted was that they won't put more money into AI, and I don't see how AI is benefiting the general public that you know, warrants taking the astronomy and physics research budget away and giving it to AI. I think basically what they're saying is they want more money to build tracking and spying tools so they can watch everybody more closely. More money to Palantir, basically. I think that's what they're saying. This is potentially disastrous, as you can imagine. And these cuts were announced by the Astronomer Royal, Michelle Doherty, who you might be familiar with from the Sky at Night. And she's quite often on there. And Robert Massey, the Deputy Executive Director at the Royal Astronomical Society, described the cuts as the worst outcome for the field in decades and the deepest percentage cut in at least a generation. Now, it's actually got worse since this article was published, because what they're now saying is the 30% will only be an average. Some departments and organizations might see cuts of 60%.
Oh, wow.
So going on, at least you guys have a monarchy. I mean, sell a castle or two.
Oh yeah.
Maybe not.
We don't have a monarchy.
Well, okay, we do now. We do now, but
Yeah. Okay. Thanks. I mean, let's face it.
Yeah, absolutely.
sorry.
I hear the Queen's got a new movie out. Yeah. So this is pretty disastrous. Now, I've been looking into whether any pushback is being organized against this, because there has to be pushback against this. There's nothing official yet in terms of what, you know, you as humble citizens can do to push back on this. But we will keep an eye on it. And if there are any petitions or any movement or any protests or something that you can take part in, we will, of course, let you know. But it's an absolutely disastrous proposal. It is only a proposal at the moment. It's not written in stone. It's not a law or anything. So we will see. We'll follow this story and keep you appraised.
It's ridiculous. We're just one aircraft carrier away from colonizing Mars. That's
Exactly.
that is all it takes. Okay, I've said my piece. Well, I'll say some more later.
Yeah. So has anybody got any comments about that? You know, other than it's absolutely disgraceful and what the hell are they doing, obviously.
Yeah.
But
Right in my mouth.
viewers, if you have any comments, please put them in the chat, obviously. So we will see how this goes, and we will keep you fully appraised of the situation. People power does work, because if you remember when the BBC were going to cancel the Sky at Night, and there was such a massive pushback from the public that they backed off. Hopefully we can get some public action going there. We might even start it ourselves, get a campaign going. Space Oddities, which I think is a good idea.
Some years ago, under the Obama administration, they tried to cut all of the NASA education and public outreach programs, as well as programs from other agencies. And there's a big public outcry, a lot of letters written, and they stopped it.
Yeah.
The public,
wow.
people have power.
People power. Okay, let's move on. Next story is quite extremely interesting. Oh, something what happened there. Sorry about that. Anyway,
Nice, though.
That could have been worse.
it's all going very swimmingly well, isn't it? So tonight I'd like to bring you this image. I don't suppose anybody knows what they're looking at. Any guesses, team?
Z14, is that the
A proplid, maybe?
Well, Z14 might give it away.
Is that a proplid?
Oh, Z14.
Yeah. 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 Z14 is the redshift.
Ah.
Oh.
What you are looking at is the furthest object ever seen by humans.
Wow.
Oh boy.
It's a galaxy, MOMZ14. It's actually 14.4 if you want the exact redshift. And this is the furthest thing that we've ever seen in the universe, as seen, of course, predictably by the James Webb Space Telescope.
Wow.
And this is it. So we're looking at it as it was 13.53 billion years ago. So we are only a couple of 100 million years after the Big Bang.
Wow.
This galaxy, which is about 300 light years in diameter, is incredibly well formed for something that is this recent after the Big Bang. And again, heads are being scratched because something this well formed should not exist this early after the Big Bang. And,
it's asymmetrical, Andy. I wonder if we're seeing one object or two.
It could be.
Just a thought.
But this is amazing that we're looking back to just a couple of 100 million years after the Big Bang, and we're seeing this proto galaxy, they're calling it. But yes, it's asymmetrical. It could be two, couldn't it? So this is absolutely amazing discovery, and again, it throws our understanding of galactic evolution into question, big time.
Here's a question, Andy.
Yeah.
So, given that some astronomers talk about the cosmic horizon where things kind of reach so far that they become invisible, maybe this isn't the oldest thing that we've seen so far, and that's maybe why it looks so well formed.
There are almost certainly earlier things, but this is as far back as we've managed to go up till now. Now, because of the expansion of the universe, it's not 13.53 billion light years away. Because of the expansion of the universe, it's now 33.8 billion light years away. So we're looking across incredible distances to see this. So there we are. So this is the new record holder for the furthest object ever seen in the universe. I thought that was absolutely lovely. Okay, lovely image from Chile this week. Look at this. This is inside the extremely large telescope.
Wow.
This is where it's going inside the dome. And what you're looking at is the mirror cell, where the primary mirror in all of its, I think it was 98 segments, will be installed. And above that, the tube on top of which will be the secondary mirror. This is actually quite a complicated light path for this telescope. There are actually 5 mirrors in the light path, and the light actually comes out of the bottom eventually. But I think this is amazing, and look at the size of this dome. It's absolutely enormous. Of course, it's a 39-meter primary mirror and a 15-meter, I think, secondary mirror, if I remember rightly. And the size of this. Unfortunately, the European Southern Observatory have pushed back the date of first light due to a few complications they've hit, and we're now looking at initial light without all the scientific instruments in about 2028, but first light with all the instruments working in about 2030. So we've got about 4 years to go. Yeah.
That's insane.
But you can excuse me. But if you want to, and it's not easy to get a scale here, but there's a guy in a cherry picker on the left. I don't know if you can see that. So this is the biggest telescope ever built by humans, and it's going to have, they reckon, about 15 times the resolution of the Hubble telescope, and make and it should be able to image exoplanets directly with this telescope.
Wow.
So we're really looking forward to this European project. So there we are. So that's a lovely image. And then
before you go on, I'm looking at an architectural diagram of the ELT. And what I see is that, yes, it does have a Cassegrain, well, not exactly a focus, but light does come out the back of the telescope. But it looks to me like a Coude focus telescope, where the light actually converges out the altitude axis.
Right.
Which would be great, because then you can put anything on it you want. You don't have to worry about weight.
That's right. That's right. Yes, it's off-axis focusing, if you like. So they've got these enormous instruments lined up. One of the spectroscopes for this is the size of a huge van. I mean, it's massive. Right. But you're right. It's at the side, so they won't have to put any weight on the telescope itself. So this is going to be fantastic as a design. So we shall look forward to first light from the European extremely large telescope in Chile. Now, the next story needs a bit of context. I want to talk about Elon Musk. Now, as you may know, for years, basically since SpaceX started, he's been talking about building a colony on Mars. And then that idea grew to a city of 1 million people on Mars. And then it just got a bit out of hand. A city of 1 million people on Mars ain't going to happen this century or possibly the next. So, it's a stupid idea. It always was. Going to Mars is not ridiculous, of course, but building a city. So he's changed his mind. So let me tell you what he's decided. He's decided that instead of building a city on Mars, he's going to build a colony on the moon. And let me give you the details. So this is his latest thing that didn't quite work out, along with the self-driving cars, the Hyperloop, the robots, the Mars colony. He's now settled on a moon colony. And let me read you what he said. The priority shift is because I'm worried that a natural or man-made catastrophe stops the resupply ships coming from Earth to Mars, that is, causing the colony to die out. We can make the moon city self-growing in less than 10 years, but Mars will take 20 plus years due to the 26-month iteration cycle. That's what matters most. There is also an AI bonus element. Yeah, right, Elon. But the prime directive must be ensuring the long-term survival of consciousness. So what he's saying is, building a big colony on Mars, what happens if the resupply ships can't get to Mars and the colony just basically dies? But of course, on the moon, it's a lot closer. So, a lot easier, I guess.
I think the AI element he was talking about was putting servers on the moon, I think. So
it will enable him to make more money out of AI. And instead of having images of child sexual abuse on Earth, he'll be able to do it on the moon. So
here we go.
Yeah.
Here we go.
So there you are. So Elon's changed his mind about Mars. He's now going for the moon. Do we believe him anymore? Of course we don't. He is, after all, full of it, as they say. So there we are. So anyway, that's the news for this week. So I hope you enjoyed that. And let me just get out of where I need to go. So there we are. All right. So that's the news. We're going to move on now. Anybody else want to say anything? Oh, hang on. That's bad. Oh, stop that. So anybody want to say anything about any of the stories in the news before we move on? No? Okay, fair enough. Well, we'll move on. Okay, we're going to go walking with planets now. And let me just tell you what this is all about. So this is all to do with the fact that the human brain cannot visualize large distances. So if I said to you, visualize 500 miles, something that's 500 miles away, you'd probably be able to do it without too much trouble. 1,000 miles? Yeah, probably. 2,000? 10,000? 50,000? And at some point, your brain just shuts down and you cannot visualize how big those distances actually are. So when we get up to things that are millions of miles away, or billions of miles away, or light years away, our poor simian brains are just not equipped to deal with us. Now, let's be honest here, up until about towards the end of the 19th century, most people never came into contact with numbers that are bigger than hundreds or thousands, So we've only had to deal with these large numbers relatively recently, and we're not good at it. So you can say to me a light year is the distance light travels in 1 year. Yeah, fine, but I can't actually visualize that. I've got no context for that. I've got no personal experience of that. And if you've got no personal experience of something, you find it very, very difficult to visualize it. So I thought about this and I thought, well, let's do it in an easier way. And hopefully it will help you to visualize large distances. So let me just get onto this. And okay. So here we are. Here we have, I present. If it comes up, there we are. Walking with planets. Okay, so let me tell you what we're going to do. We are going to judge these distances and visualize these distances, something in our own experience. We're going to ask, how long would it take you to walk to each of the planets? And what we're going to do, we're going to assume, first of all, we're talking about the mean distance to the planets. We could have gone with the minimum or maximum, but I've gone with the mean distance to each planet. And we're going to assume a walking speed of 3 miles an hour with no toilet breaks. So you need to go before you set off, basically. And put a note out. Put a note out for the milkman because you're probably going to be gone a while. Okay, so let's go on to the first one. I'm going to include the moon in this as our first target because I think that's a sensible place. Excuse me one moment. Sorry about that. That keeps popping up for some reason. Right. So we're going to go to the moon first of all. So how long do you think, guys, it would take you to walk to the moon? Viewers, if you've got any guesses, you can put it in the chat, of course. Anybody like to guess how long it would take you to walk to the moon?
45 days.
45 days.
Oh gosh. 3 miles an hour, 24 hours a day, huh?
Okay, well, in actual fact,
75.
to walk to the moon, it would take you. Oh.
These people are hogging. Might as well just let them do.
I'm terribly sorry. Got a technical bug coming. Anyway, the answer is 9 years.
Oh my goodness!
Yeah, okay.
How's that all?
That was close.
to walk to the moon, which is doable, isn't it? I mean, so it's definitely doable.
Not if you don't get to go to the bathroom. I'm sorry.
Okay, so the mean distance is 0.239 million miles, or 239,000 miles away. In terms of human lifetimes, that's about 1/10 of your lifetime, obviously, to walk to the moon. And if you were arriving at the moon now, having walked for 9 years, you would have left, of course, in 2017. And what do we have happening in 2017? Well, we had the first gravitational wave detection of a binary neutron star merger, which you may remember, the famous GW 170817. And it was the dawn of multi-messenger astronomy. So that's what happened in 2017. Now, we're going to move on, obviously, to Mercury. So how long do you think it would take you to walk to Mercury?
Oh boy, let's see.
120 years.
120 years, right? Any other guesses?
Higher, lower, higher, lower.
Good game, good game.
Pretty higher.
1,000 years.
Right, okay, so to walk to Mercury, it would actually be 2,168.
Wow.
Yeah.
Yeah.
Doable.
Okay.
That's doable.
Is that when it's closest to us or far beyond the sun?
You're not listening, are you? I did say mean distances.
Okay.
There's always one. There's always one. Yeah. So mean distance of 57 million miles. That's 27 human lifetimes to walk to Mercury. If you were arriving there today, you would have left in 143 BC. And this was the height of the Roman Republic following the Punic Wars. Carthage was destroyed and the Mediterranean dominance was secured. So that's how long it would take you to walk to Mercury. The next stop on our walking tour, ladies and gentlemen, is Venus. At a mean distance of 25.7 million miles. Any idea how long this would take you to walk?
1,000 years.
You're very close. It's actually 978 years.
Wow.
Yeah, good guess.
Mm.
That's
Very good
12
guess.
human lifetimes. And if you were arriving there today, you would have left in 1047 AD, which was, of course, late Anglo-Saxon England shortly before the Norman conquests. So that's when you would have left if you were arriving there today. Now, I hope this is a bit more meaningful than millions of miles, which is very difficult to visualize and understand and come to terms with. Okay, we're going to go to Mars now. Off to Mars. Hope your feet aren't getting too sore. Mean distance of 48.7 million miles. The time to walk to Mars from the Earth is 1,852 years. That's 23 human lifetimes. And if you were arriving there today, you would have left in 174 AD, which was the height of the Pax Romana under the Emperor Marcus Aurelius. Philosophy, prosperity, and imperial zenith. There you are. That's when you would have left if you were arriving there today. On to Jupiter at a mean distance of 391 million miles. But what's important, that obviously you can't really visualize. Anybody like to guess how long it would take to walk to Jupiter?
5,000 years?
5,000 years? Any
4.5?
other?
3,000 years.
6,000 years. To walk to Jupiter would actually be 14,000
Oh.
years. 186 human lifetimes. If you were arriving today, you would have left in 12,840 BC. This was the onset of the Younger Dryas cooling event near the end of the last ice age. So if you had left Earth towards the end of the last ice age, you would just now be arriving at Jupiter. So,
And you'd be cold either place.
absolutely. Okay, so on to Saturn. At a mean distance of 795 million miles. Any guesses about this?
It's got to be more than
30,000.
30,000, yeah.
Yeah, more than that.
That's a very, very good guess. It's 30,260. So well done.
The answer is 30,000. You check your numbers. Yeah.
Yeah.
30,000 years in 4 days.
Yeah. And this means that if you were arriving there today, you would have started walking from the Earth in 28,234 BC. This was the era of Upper Paleolithic cave art and advanced stone stool cultures across Europe and Asia. So there we are. Right, on to Uranus.
60.
60. Any other guesses? Right,
Yeah, I'll go with that, Lou.
It's a mean distance of 1.694 billion miles. Time to walk 64,441 years, which is, 60 is a good guess.
Okay.
If you were arriving today, you would have left at 62,421 BC. Modern humans spreading across Eurasia, Neanderthals were still present in Europe, coexisting with our ancestors. So,
Yes, but
Some
were
are still
people
alive
people
today.
walking? Were there bipedal people walking at that time?
yes, absolutely. Yes.
Okay.
Right.
Hopping.
Okay, let's move out to Neptune. Neptune at a mean distance of 2.607 billion miles. Any guesses?
230,000 years.
Well, it's 103,000 years.
Oh, for goodness sake.
That's 1,287 human lifetimes. If you were arriving today, you would have left in 100,941 BC. Early dispersal of Homo sapiens out of Africa into the Levant, the beginning of humanity's global journey. So there we are. Yeah. Okay, and I have included Pluto, of course.
Hey, woohoo!
Because he's
So, Pluto at 3.577 billion miles mean distance. Any guesses?
It's going to be half of that. So
210.
60,000.
The
210,000.
Right, it's actually 136,000 years, just over. If you were arriving today, you would have left in 134,090 BC. The emergence of anatomically modern humans in Africa, as our species taking its first steps on the Earth. So,
wow.
Yeah. Okay, so can we go any further than that? Yes, we can, because we're going out to the inner edge of the Oort cloud.
Oh boy! Wow.
That's a fair long walk. That.
Oh man.
50 million.
Jeez, inner edge of the Oort cloud.
Right, it's got. I have to say, this distance is not known.
Right.
It's estimated at a mean distance of 185.8 billion miles. But there are various models that go higher than that. The answer is we just don't know. I'm sounding like Patrick Moore. The answer is we just don't know. So the time to walk it is just a tad over 7 million years. Which meant you would have left 7 million years ago, 7 million BC. Early hominid evolution, upright walking ancestors long before humanity existed.
So 7 million years is so much easier to visualize than
well,
however many billion miles.
Yeah.
But look at it this way: dinosaurs would have gotten there hundreds of millions of years before.
Yeah, true. It's 7 million years is actually 88,384 human lifetimes.
Wow.
Yikes.
Yeah. Okay, can we go any further than this? Yes, we can, because we now go to the outer edge of the Oort cloud. And the estimated distance for this is 9.3 trillion miles. And the time to walk. Anybody want to take a stab at this?
Oh my Lord.
65 billion years.
Well, it's actually 4.4 million human lifetimes, and that works out to 354 million
years.
Yeah,
Wow.
this was in the early Carboniferous period. Not long after the Devonian Carboniferous boundary.
Was that on a Thursday?
Yeah, it was. Yeah. And amphibians and other early tetrapods were diversifying on land and in freshwater. It was the age of fishes. Conditions had only recently given way to more complex land ecosystems. So there you are. So that we've walked the entire solar system now. And I hope that has helped a little to give you an idea of the distances and the times involved, viewers. So there we are. So that's
mad. That's mad.
Yeah.
Wow.
Yeah.
So there we are, walking with planets. Now, talking of planets, Lou's going to tell us a bit about some yardsticks we can use for the planets.
Yes.
So let's just put this up for you, Lou. There we are.
Great. Well, I'll tell you, after that, Andy, my head is just swimming. I can barely concentrate. I mean, on the one hand, the amazing graphics that you put up there,
Oh, thank you.
and the other is how much free time you must have on your hands.
This is one of the benefits of retirement, Lou.
Oh, that's how it works.
Yeah.
Well, maybe I'll just march upstairs and quit my job at Marymount. Say,
Yeah, you need to do that. You definitely need to do that.
well, so Andy begins with a very important premise, and that is it's very hard to teach in any relatable sense distances in the universe. I mean, Andy went out to the, by some measures, the end of the solar system. And of course, that's a tiny, infinitesimally tiny fraction of distances that we talk about. So we use we try to use different yardsticks or meter sticks to make these numbers a little bit smaller, a little bit more digestible. So in the solar system, we often talk about the AU, the astronomical unit, which in fact was the holy grail of astronomy for centuries. How big is the solar system? How far away is the sun? And the AU is the average distance between the sun and the earth. It's about 149 million kilometers, about 93 million miles. And so that is 1 AU. So then Mars is out at about 1.5 AU, and Jupiter's 5, Saturn's 10, roughly. So it's a lot easier to use those numbers. When you get outside the solar system, though, we start to use much larger yardsticks for the distances to stars and eventually galaxies. So, for example, we use the light year, right? And let me ask our viewers, what is a light year? Just type it into the chat. You've heard of this before. What is a light year? Let's see what we get here. Our viewers. I hear the neurons firing out there. Must definitely be.
Anybody? What's a light year? Somebody in the chat, tell us what a light year is. No.
Okay, perhaps it's good that we have this little educational moment. So let's see. Michael says distance light travels in a year. Sandra says a group of us from North Wales Astronomy did a solar system scale model. Solar system light travels a year. So no, actually a light year is pretty much like a regular year, only it's less filling. Light is pure calories in a light,
Good for the diet.
Yeah, yes, good for the diet. Okay, so there are lots of ways to approach this idea of teaching distance, and one of them is to build a scale model solar system. The one I'm showing you here is from the Jet Propulsion Lab website, where they do a lot of education and public outreach. And this is one scale model solar system that they've built. Let's see here. If I go to the next slide. And it begins with finding the scale that you want to use. So you might decide that, so in this case, for example, 10 centimeters is 1 AU, right? So roughly speaking, Mercury is out at 3 or so centimeters, Venus is maybe 7, the Earth is at 10, and Mars is at 15, and so on. And so that's your scale. And so you begin with knowing what the actual distances are and then ratioing those to the scale that you want to use. In this case, the attempt is to make kind of little kind of beads on a string that are the right relative distance apart. And this always kind of, I found that for the students that I teach, it surprises them. The inner solar system, the terrestrial planets are so kind of bunched together. And the outer solar system is so widely spun out. And then we talk about how that wasn't, the positions of the planets as they are today were not always the places that they were before, which is the grand tack model of the evolution of the solar system. And you just, things get kind of crazy. So here's a how-to on how you would string different beads of any of sorts that you can pick together in order to make a small, scale model solar system you can put in your pocket. And so that's great because it's portable. I've got a dear friend, Dave. I don't know if do you know Harold Williams?
Oh yeah, sure.
Yeah. I think he's still the planetarium director at Montgomery College in Tacoma Park.
Yeah, I think so.
Right?
Yep. I think so.
And he has a little medicine bottle, and he puts little peppercorns and acorns in there that reflect the actual sizes or relative sizes of the planets. And he'll go walk down the sidewalk and drop one with his students, and he'll sing a song, "The Family of the Sun, Family of the Sun." And he's a little crazy, but that's great. That's how you teach. So it doesn't have to be on a string. You can have distances with, as you see in the middle picture here, with chalk on a sidewalk, turn it into a real art project. And you can do all kinds of scales. And it turns out that this is being done lots of places in the United States and around the world. I'll show you some of that. So, okay, well, stepping back, Earth is a peppercorn, which I think is his kind of medicine bottle solar system. And what they do is they start with a soccer ball. Well, okay, you guys call it a football, right?
It's the round one.
The round one, right?
The round thing. Yeah. The thing you kick around when you're not kicking around your friends. With 8.64 inches in diameter. So then, if that were the case, how big would Mercury be? Well, it'd be about the size of a pinhead, and Venus would be a peppercorn. Venus is 95% the diameter of the Earth, so peppercorn there again. And you go on and on up to, let's see, Jupiter is a pecan. Okay. So, and then from that, you can actually continue with the scale model, not just with relative sizes, but with distances. And so here you can pace off that Mercury would be 10 paces, roughly 10 meters, let's say, from the sun, and so on, all the way out to an average Pluto, which would be, so Pluto varies actually between 30 and 50 AU. So that's probably for 40 AU, I'm guessing. Let's see, Saturn's at 10, Uranus 30, 10, 20, 30. So here actually, in this case, Pluto is at its position when it is inside the orbit of Neptune. Aha, interesting. So, and then you can make up these fact charts for it. So you're not going to see anything like a pinhead too easily, but you can make these fact charts up and you can place them along the scale model solar system. So this is a great project for Boy Scouts and Girl Scouts, for depending on the level that you teach at, everything from elementary to high school and beyond. The picture in the upper left here is right outside the National Air and Space Museum in Washington, D.C., the most visited museum in the world. And Dave, you know him, and I can't think of his name. He used to lead the infrared planetary science group at Air and Space. I don't remember his name now.
Jim Zimbelman. I'm not.
That's not
Tom Waters. Jim Zimbelman. Okay. Anyway, go ahead.
Anyhow, he got a NASA grant to do this, and so spaced along the sidewalk here are planets with fact sheets, and it's actually quite a large distance.
And it's accurate.
And it's accurate. It's accurate.
Although you can tell. So this is what you can do. If you, I mean, the sun is the scale size, and the distance to the Earth is the scale. If you stand by the Earth, and you kind of put your finger up at just the right distance to cover the actual model of the sun, which you can see, it's not that far away in the distance, and then you hold it up and block the actual sun. You can see it's the same size, basically, right?
Right.
In other words, the scale is anyway, it's kind of cool.
Yeah.
It's kind of
About half the diameter of your pinky finger, it turns out.
Yeah, and you can see it. You can, yeah.
And then, okay, time for public service announcement. Don't do this with the sun. Okay. And so you can see all kinds of examples of scale model solar systems. The one in the lower left, I think, was in Tucson, Arizona, I think. And I don't remember where the other two were. You can use a football field. You can scale the solar system to 100 yards, roughly 100 meters, putting the sun at one end. And, the sky's the limit, as they say.
The middle one is from my website, Lou. The middle lower one is.
Is it really?
Yeah. Anthony, oh gosh, I can't remember his name. He put that together, and he did this with some school children. But I have one set up on my website, which you used to be able to get to before the Department of Defense came along, and you can do this same thing. You can print out them at the scale sizes, and it tells you how far. How far you to walk, where you set them up in a field, or you can see it in a parking lot. Anyway, I'm interrupting you. Go ahead.
I didn't know that was yours, Dave. I'm glad you spoke up.
Yeah, that's cool.
What I find amazing about that picture is you appear to have 20 or 30 elementary school students actually obeying rules rather than running around like crazy. But that's cool. That's cool. There are other things that you can do to teach about the size and scale and other parameters of the solar system. And one of my favorites is to have students develop a solar system travel brochure. So they pick an object in the solar system, from the sun to comets to Jupiter, whatever, any object in the solar system. Then they have to go learn about it. And then it becomes a visual arts project, so they can clip pictures from various places or do their own artwork, and then have them stand up in front of the class or the Girl Scout troop or wherever you are, and give the pitch. Why should we visit the Earth? Why should we go to the sun? Because you can have a hot time at the Plasma Cafe or something like this. And they're amazing. I've kept some of mine from when I used to run the elementary school after school astronomy clubs. They're very creative. So this is a great way to have fun, have some visual arts and language arts, and teach students about the solar system. Here's just one of my students did. Where are they? Neptune. Okay, and look, they all this great artwork. So. And they even came up with an acronym for Neptune. Naturally excited, pumped up, terrific, unknown, never-ending experience. Okay.
That's great.
Story of my life.
Put them on the president's PR panel. They need some help. I just thought this one was great.
That is great.
Is it Mercury? It won't be that.
A bit like visiting Cumbernauld.
Yeah, and you can get online and type in solar system travel brochure in Google or your favorite search app, and get some more information about how to do these. I generally do them as trifolds, but you can design it however you like. And finally, or almost finally, my wife and I were in Iceland back in October. And I took this picture. Believe it or not, it's high noon in Iceland. And I just thought that was so cool. Or maybe it was 1 p.m. It was between 12 and 1 p.m. So the sun's not very high in the sky. But even in Iceland, we were staying in Reykjavik, and they had a scale model solar system. and they had this kind of aluminum ball that is the sun, and then at the right distances they had these placards with information, and they also had the actual relative sizes based on the size of the sun here. And I tried to blow it up in the top right to show that this is Mercury, how big Mercury is. I mean, it's like a tiny pinpoint. I couldn't even blow it up enough, but they've got it kind of sitting on the top of this cylinder that's in the ground. So all around the world, people are doing this. You can do it too. It's pretty easy, and hopefully you'll get a better idea of what the solar system is about as well. That's it.
Fantastic. Thank you very much indeed. Well done, Lou. Yeah. These are things worth doing. I mean, I've done this sort of exercise with children in playgrounds and, other things. So, anybody wanting to learn a little bit about scale and distance these things are very, very useful to do with people who are interested in astronomy, especially children, of course. So there we are. So thank you very much, Lou. Paul in the chat asked a question earlier. Just imagine how long it would take you to walk to the nearest star. The answer to that, Paul, is that to walk to the nearest star, Proxima Centauri, would take 951 billion years. So that's answering your question. So nearly getting on for 1 trillion years to walk to the nearest star. You'd go through a good few pairs of stars.
Use this as a preview that in November we're going to be having a special, I don't know if the whole show, but a special segment on Voyager, because in November, Voyager, traveling at about 3 AU per year, Voyager 1, will be a whopping 1 light day away.
Right.
Yeah.
After 50 years in space.
So we will be doing probably more than one program involving Voyager when it gets to November for the 1 light day distance of Voyager. So we got that to look forward to. Deep Burrito, I'd like to say thank you so much for your exceptional generosity. That's very, very kind of you, so much appreciated. All goes towards keeping us going. So thank you so much. You're very kind. We do appreciate it. Okay. So what have we got now? Well, actually, now we have something new on Space Oddities from our very special guest this week, Miss Williamina Fleming, otherwise known as Tom, of course. What Tom's going to be doing, I think we said once a month, didn't we, Tom?
Yeah. I'm happy with that. Yeah.
Once a month, Tom is going to be giving you some guides to image processing your astronomical images that you've taken with your telescope or indeed with your phone. So we'd like to do this because we know many of you are sort of setting out on the path to astronomical imaging, and we thought it might be useful for Tom who's knows a little bit about it anyway, to teach you a little bit about how to process your astronomical images. So I'm going to leave you in the very safe hands of Tom now, and take it away, Tom.
Okay, you probably built that up just a wee bit too much, Andy, but let's...
Okay, right, we're going to do a section on image processing from Tom. It's going to be useless, so you may want to while we get through this, just go take a break or something. So anyway, is that better, Tom?
Much better, yes.
Right,
better.
okay.
Let's set the bar at the right level, I think.
Yeah.
So I'm guessing you can see my screen okay?
Yeah, it's a little. I don't think we can actually read much of what's on it. It's a bit.
Okay, that's fine. I mean, most of this probably doesn't make that much sense, even to me, to be perfectly honest. But so the software that I use to process my images is called PixInsight. It has quite a large learning curve, but there's other software available like Photoshop and even what's the other one? GitLab, I think it's called. And there's some other kind of free bits of software as well, but I use PixInsight because it's quite a powerful tool. But what I normally start off by doing is loading in all of my subframes. On this occasion, we are doing the Tadpoles Nebula, NGC 1893, IC 410, I think, probably. So to fact check that, I'm pretty sure that's correct. So what I normally do is start by loading in all my calibration frames first. So I'll start with darks, which help get rid of some of the inherent noise in the cameras. I use a monochrome camera. I also input all of my flats, which help mitigate with any vignetting if it's a bright moon, or if your neighbor has an annoying security light. This kind of helps do that and helps mitigate that. I also load in all of my lights, and I'll go through some. I won't go through all this software because it could take forever, but it gives me a rough indication output of, in this instance, I use hydrogen alpha, oxygen 3, and sulfur 2 filters, which then get mapped to RGB. And in this instance, there's about 23 hours worth of data. All of this is trying to mitigate the signal to noise ratio. The more time you have on these objects, the better signal to noise ratio you have. I won't press play on this because it'll take about an hour. But once all that is through, it will then stack all those images. I'm guessing most people know what stacking is, but we take lots and lots of light frames, lots of exposures, digitally stack them on top of each other, to give, in this instance, to give us 3. I should have switched that off. Hold on a second. Let's switch that off. And these are the 3 output files that PixInsight will give me. And I'll zoom into this a little bit, but you can see it's just a black frame. There's nothing really much there. Same with that one. I don't know if you can see that at all. But then you can't really see that, Andy, can you? No.
Just a few stars I can see.
Just a few stars, yeah. What I then do with these subframes, I do it a couple of ways sometimes. I'll extract the stars and then process the stars and the master lights separately, but just for speed, I have processed them with the stars. And what you can do in PixInsight is the same that you would do maybe in Photoshop, is do what's called a histogram stretch, which allows you to see exactly what is contained in these stacked images. You see the top one is the oxygen filter, the top right one is the sulfur, and the bottom one is the hydrogen alpha. Naturally, there's going to be less noise in the hydrogen alpha because it's more abundant. Sometimes there's a little bit more noise in the sulfur, because depending on so this is an emission nebula, which is the clouds of dust and gas are kind of not lit mostly by stars, but mostly it's the gases that are lit, or illuminated, sorry. And that is the oxygen. So what I can then do from here, let's hide those. I can then do what's called a channel combination. And keep in mind, this is very specific to monochrome imaging. One-shot color imaging, or even the data you get from a smart telescope, is a little bit different. I know smart telescopes kind of stack and process it for you, but you can export those files from a little smart telescope and you can import them into PixInsight or Photoshop or whatever it may be. I then do a channel combination, so I align each of these master stacked images, and ignore that error. And I drag these little things over here, I combine them into the sulfur gets matched to the red channel, the oxygen gets mapped to the blue channel over there, and the hydrogen gets mapped to what's going on with that? The hydrogen gets mapped to the green channel. And what that then does, once I hit play, once I hit that little button there, is it gives me a final stretched image, and it looks really green. Actually, that's just the nature of how these kind of cameras work. It's more prevalent in one-shot color cameras, But I've got a really clever little button here called Nuked Stretch, which gives me a final, well, not a final color image actually, but gives me a rough color image that shows what actually is contained, what the color data is contained within this image. What I then can do is I'll take that, and actually just a quick note here actually, and I've done a little bit of exercise on scale as well. You can see the tadpole, so this whole emission nebula is called the Tadpoles Nebula. I think this bit here is called NGC 1893, and then there's a little bit up here which is called IC 410. But these Tadpoles Nebula here, they do look like tadpoles. They look like other things actually, but it's a family show. They look like tadpoles. So the distance from roughly there to that point there is 10 light years in length. So that shows you how vast these things. And I just asked ChatGPT a second ago how many Earths would fit end to end in 10 light years, and it's 7 billion Earths. So I can't work out how long that would take you to walk, but probably quite a while. What I then do once I've got this, so this is what's called linear data. So linear data means that you can work non-destructively with it before you set all of those parameters and all those processes in stone. But what I can do from here, if I have combined all the master stacks together, is I can extract the stars. Let me just double click this. And so what I end up with is a starless image on the right hand side and the stars on the left hand side. And I use the software again to then combine that later on. But it means that I can work on the starless image separately. Some astrophotographers and astronomers then further down the line, actually maybe even part of the same imaging session, they do RGB stars separately, but I'm quite lazy, so I don't do that. I just do it as one kind of complete process. But what I can do is I can then work on that image separately. And I'm going to show you what. So with a lot of fettling, a lot of color balancing, and a lot of noise reduction, and a lot of other kind of things in between that, I end up with what I think is a final kind of output of this image. And it highlights all the faint dust and gas and all those kind of cool things around about it. So that's almost 10 minutes, Andy. I don't know if anyone has any questions. I'm pretty much finished. I don't think I can. I could go into a lot more in-depth stuff, but I'm not sure.
Well, let's leave it like that for now.
Yeah, I'm not sure if it's relevant just now.
And viewers, if you have any comments, or if you would like to see more image processing tips, then tell us in the chat, because this is a bit of an experiment, as it were. Yeah. So if you have any comments, would you like to see more of this sort of thing on Space Oddities, or what would you like? So if it's useful to you, please tell us in the chat. If it's not useful to you, then please tell us as well. There's already a comment from Paul in there. If anybody got any other comments, please put them in the chat. Tell us what.
That was a whistle stop tour. That was very much a whistle stop tour.
So yeah, tell us if you would like to see more image processing. Then tell us. You are our viewers, and we'd always try to give you what you would like to see. So thanks for that, Ian. Any other comments? Please tell us, and we will listen, obviously. So yeah, we're getting some positive comments in. Ian says, very interesting as a starter. Sandra says, great, Tom, thanks. Derek says, thanks, Williamina. So there you are. Paul says, there are already a zillion, hang on, I've lost it. There are already a zillion image processing videos. Your time might be better spent focusing on basic astronomy news and concepts. So there we are. Thank you for that comment, Paul. And anybody else got any comments? We will listen. Of course we will, because it's your show. So we want to give you what you would like to see. Stuart says, yes, please. Mike Beer says, brilliant. So there you are. Thanks for your comments.
Very good.
That will help us. Okay, right. What we're going to do now is going over to Dave, and Dave has, as you probably know, does a weekly look back in time to interesting events in the past. So what have we got for this week, Dave?
Okay. Yeah. Well, it was an interesting week. Even harkens to some of the things that we talked about a little bit earlier. And of course, I need to get it set up so I can share the screen with you. All right. Hold on one second here. Yeah, there we go. All right. So you should be seeing this in a moment. Yeah. I hope.
I've just put it up. So there you go.
There we are. Oh, okay. Now you said I should make this full screen then. All right. Give me a second.
What is that you're using there, Dave? What software?
Now, everything's gone. That's just the Gamma software, but I'm putting it in.
It's Gamma. Right.
Just to show it made a PDF out of it. Is basically what it did. But unfortunately, I am not getting. Okay, here we go. Oh boy. Sorry. All right, it's taking its time here. Okay, it's grinding away. It will. It should go up in a second. Sorry. All right. Well, okay. It is up on my screen, and I guess there's a little bit of a lag.
Just put that supermarket music on again, somebody.
Yeah.
Hang on. Let's.
All right. Yeah. Well, I know. I noticed every time you started sort of humming, and your music came on. There you go again. See?
Are you ready? Okay. I just put some music on for you. Okay.
Okay. It should be, but it's not. All right.
Okay. No, it is. Just give me 1 second.
I will try again. All right. Well, we got the week of February.
Leave it with me. It should
February
be
8th through 14th. Share the window. Share this window. I don't know what it's doing.
Hang on. It's coming. There
Okay.
Okay. There you go.
See it. There we go. All right. Okay. So, February 8th through 14th. Kind of interesting stuff and kind of oddly sort of related. A few things related to each other, which is kind of funny, but you'll see what I mean. So February 8th, 1969, the Allende meteorite falls in Pueblito de Allende, Mexico. This is turned to be really important for a number of reasons. First off, the largest carbonaceous chondrite ever found, and carbonaceous chondrite meteorites are basically some of the most primitive substances in the solar system. I mean, it's basically stuff that formed at the very, very beginning of the solar system and it didn't get incorporated into other bodies. It didn't get melted. It didn't get, it's unaltered. So it's really a really nice, snapshot of the early, very, very, very early solar system. And this was the largest one ever found. It was a fireball. It was seen exploding. It also one of the largest strewn fields, which is the area that pieces of a fireball, when it explodes in the atmosphere, land. And it covered something, 500 square kilometers. I mean, a huge area.
Wow. That's a big
Wow.
Yeah, in Mexico. Yeah, the place where it fell is about 500 kilometers south of the border with the United States at El Paso. So the center of it, or where this Pueblito de Allende is. But anyway, it was everyone's lots and lots of people saw it. It was quite a spectacular fireball, apparently. And the Smithsonian sent a bunch of scientists there. And what they did was they actually told the local school children in the town that they could get free soft drinks if they brought them samples of this meteorite. So, of course, all the kids rushed out and got the samples. I don't think any of the kids brought back the 110 kilogram one, but maybe that one's pretty obvious. But I believe that's probably what's in this picture that shows some of the local people there and one of the bigger chunks of the Allende, if not the biggest chunk. Turns out that that because they have so many samples of it and because it's so primitive, the Allende has become the sort of standard benchmark for solar system composition. In other words, now when they look at the composition of anything else in the solar system, either slightly altered things, pieces of asteroids, or any, any chemicals, fingerprints of any type that they measure, they usually compare to the Allende meteorite as that's the standard that everything started with. And now, oh, this has more carbon, or this has less nitrogen, or this has that, and then they make their sort of histories of what happened to this material based on how different it is from the Allende meteorite. Now, the other thing that was really fortuitous about this was that, and you see the date, February 1969, they had just finished basically setting up the Lunar Sample Receiving Lab in Houston at Johnson Space Center, which was a, it was the state-of-the-art lab for studying samples, because they were preparing it to get the lunar samples back. And of course, it was the, completely clean, completely, filters. They knew that this would be the, because they wanted to have the lunar samples, absolutely uncontaminated, and they had the best equipment to look at the samples, and they brought the samples there, and so they actually got to study this meteorite with the state-of-the-art, the best equipment that was in existence at the time, but also it allowed the people in the receiving lab where the samples from the moon were coming a few months head start in testing out their equipment. So it worked out really well. It was like sort of a perfect timing that this meteorite fell when it did. Anyway, that's
Wow.
pretty cool. So that's February 8th, 1969. So yeah, whoops. Okay, I'm going too far. There we go. All right. So February 8th, 1992, European Space Agency, the Ulysses spacecraft, flew by Jupiter within 400,000 kilometers of the cloud tops. And it actually used the flight. And if you can see, if you can tell in the image, it sort of shows the trajectory. It flew over the North Pole of Jupiter, and then that actually turned its trajectory basically normal to the ecliptic. So the first spacecraft to have an orbit normal to the ecliptic plane around the sun, and it allowed Ulysses to look at the sun from looking down or up at the South Pole, down at the North Pole, however you want to look at up and down. But it allowed to see those parts of the sun that were never seen before, never viewed directly before. Okay, let's see. So this is kind of interesting. 2021. Of course, the thing about going to Mars, these are 2 Mars missions, is that there's every just about 2 years is when the launch opportunity is Mars. So it's not surprising that things are arriving at Mars about the same time. These only came to Mars a day apart. The United Arab Emirates HOPE mission and the Chinese Tianwen-1 mission reached China and went into orbit. This was the first Arab interplanetary mission, and a day later, the first Chinese interplanetary mission reached Mars. So, right, 5 years ago. I don't know if this makes you feel old or not. I kind of remember it. But and the image down in the lower right there is an actual. Basically, it's taken from the live feed that was coming from Tianwen as it went into orbit around Mars. So that is actually an actual image taken from the spacecraft. With, you can see part of the spacecraft solar panels and part of the spacecraft, and then the edge of Mars there, which I just think is really cool.
Yeah.
Okay, I keep flipping too far. All right. So, February 10th, 1990, the Galileo spacecraft flies by Venus, rather, on its way to Jupiter. Comes within 25,000 kilometers of the surface. Took some pretty cool pictures. They got, not only a gravity assist to help them make its way to Jupiter, but they got to test out all the equipment on Galileo, which the scientists and the engineers love to do. They love planetary flybys just, for that reason, is that they get to turn everything on and test it out and see what's working or what needs to be tweaked. And that. February 13th, 1990, 3 days later, Voyager 1 begins taking this, what was called the Solar System Family Portrait. It started taking pictures of all the planets in the solar system. It had reached by that point, it had spent 13 years now getting out past the orbit of Pluto. And so it turned itself around. And let me go to the next slide here, just to blow up that family portrait. And it just took snapshots along where it managed to catch every planet that was, except Pluto, which wasn't in its field of view at the time. But it did manage to catch every other planet. Now, and you think about this, what that means is that Voyager 1 goes 13 years, it turns around, it takes a picture. In the frame of Venus must have been the Galileo spacecraft, which had only a few days before flown by Venus on its way to Jupiter. And so we have a spacecraft launched 13 years before, turning around and taking a picture of a spacecraft that had only launched earlier that year, and or so, I guess that's right, maybe 2 years, and would have been, if you could see it, obviously you can't, in the frame of the picture that it took of Venus, which I thought was kind of cool. Anyway, let's see, February 11th. Okay, so 1970, Japan actually only became the fourth nation to launch its own satellite into orbit. The Osumi on a Lambda 4 booster, and that's just a picture of the launch. It actually looks like a really tiny little rocket there. It wasn't such a big rocket. It was a small satellite, but a functional satellite. And it's kind of cool, though. I think 1970. So we're talking 13 years after Sputnik. Japan is only the fourth nation to actually launch its own satellite into space. Other nations had satellites launched. Italy had satellites launched by the United States, but to do everything by itself, I think France was the third. Obviously, the Soviet Union and the United States, and I think France was the third. But Japan only became the fourth nation in 1970. And then in 1961, so again, Carter points out, Venera 1, the first spacecraft to reach Venus, to fly by Venus, was launched in 1961 on February 12th. And again, we're talking 9 years later, there's only the fourth nation to launch its own satellite, and there's, meanwhile, the Soviet Union is launching to Venus. February 14th, okay, so now we're getting to the end of this week, but 2000, near Shoemaker, went into orbit around asteroid 433 Eros, which is shown there in the lower right. Almost exactly a year later, it actually touched down on Eros. It wasn't planned as a lander, but they decided to see if it would work, and it did actually crash on the surface. It made I guess the equivalent of a hard landing, but on an asteroid, a hard landing with the microgravity is not very hard. And it actually survived. It survived touching down on the asteroid, and actually was continued to transmit for a while before it finally died. And let's see. Oh yeah, and harkening back to what Lou mentioned in one of his pictures, February 11th. 1999. So 27 years ago tomorrow, after 20 years, Neptune is no longer the furthest planet from the sun. Pluto passed Neptune on February 11th, 1999. Because their orbits cross each other for a short amount of time out of the 248 year orbit of Pluto, 20 years of that is spent inside the orbit of Neptune, just because it's so elliptical. It just slips inside Neptune, inside the distance of Neptune for a little while. And Pluto did remain the furthest planet from the sun until August 24th, 2006. August 24th, 2006 was the day that Pluto was declared not to be a planet anymore, and therefore Neptune became the furthest planet from the sun. So nothing to do with orbital dynamics, but and I believe that's all I have for
okay.
Yep. Thank you.
Really interesting stuff as always, Dave. So thank you so much. That's really good. And I think the UAE being the first Arab country to go to Mars, quite a momentous event. And it has actually sort of ignited a much bigger cooperation between Arab countries with regards to exploring space. So it was a great mission. And
did you watch it? Andy, did you actually watch it when they landed? Because they did live stream it when they landed, and it was pretty exciting. It was exciting to see how excited they were. All the people in the control room.
Yeah, that's right.
All the dignitaries who were there, and it was.
Yeah, it was an inspiring event.
It was, yeah.
And it's led to. I was reading that the UAE and other Arab countries in the region, it's made them more aware of their need to do more STEM education.
Okay.
Which is a great thing, of course. So there we are. Thank you, Dave. Okay, let's move on. Let's just take a look in the chat to see if anything's popped up. Thank you all for being here this evening. And Ian says, but Pluto isn't a planet. There we are.
What it was at the time.
Well, exactly, at the time. Yeah.
Yes, it is.
Ian says, thank you, Dave. Keep it up. So there we are. So there we are. Okay, so we're going to move on now to this part of the week. Next, we're going to go to a man who needs no introduction.
Who is it?
Is he ready? Can you hear me, Mother?
Yes, I can.
Oh, okay. Okay. So anyway, we're going to go over to Roger now for our weekly look at the night sky and the viewers gallery. Now, I understand that we haven't had a good response for the gallery this week, but given the intense and persistent rain that has beset the UK for weeks and weeks now, I'm not surprised we haven't had any many new images. So let's just get this up for Roger. So, what's in the night sky for this week, Roger?
Okay, so we're working our way through the middle part of the month. Okay, we're currently experiencing the last quarter and working our way up to a new moon for the early part of next week. So things might look a little bit better. But looking south in the horizon, looking up, we'll be able to see Orion and Jupiter dominating the southern areas of the night sky. And we've almost lost Saturn at 10 o'clock of an evening that this is currently looking at. And we've got the spring constellations and the galaxies coming through, with Leo and Virgo coming up through the skies now. So we've still got Orion, still quite nice. I mean, it does look quite good as soon as it does get dark, but the nights are getting a little bit shorter now. So we'll just have to make the most of it. Right, so just before sunrise, we've got Mars coming up just a bit previous to the sunrise, and then following on we've got Venus and Mercury trailing on behind. So you can see as it does come up, they're all almost in alignment as the sun rises. But when we get down to sunset, we've got Venus and Mercury following a little bit behind, and also Saturn. So hopefully by the end of this month, Venus will be a bit more of a dominant evening object to see, as well as Saturn. But they are a bit lower in the night sky, so never mind. So we do have a lunar occultation of Tau Scorpii on the 11th, which is tomorrow. So it might be possible, should a miracle happen that sky's clear, we can get to see that. But good luck with that. We do have a planetary parade lurking behind the clouds. So we do have Saturn, Neptune, Jupiter, and Mars, with Uranus, Venus, and Mercury all around by the sun. So typically they are there, but it's not really safe to look at them with the closeness of our sun. So no doubt there'll be efforts trying to make more of what there is. So we've got a new moon on the 17th, and also then we've got the Year of the Horse, which is celebrated in Asia, notably China and so. And we've also got Ramadan beginning on that day as well. So things are happening in the different faiths as well. So look out for those. And also on that day, we've got an annular solar, but it's only really useful if you're in Antarctica, really. But I just wanted to highlight that that's what's happening in the next week or so anyway. But
I think Dave and Lou have been in Antarctica recently, haven't they?
Yeah, but not at that locations, unfortunately. Okay. Right. So this was what the sun was looking like today in various spectrums, and we do have a few of the active ones, notably 4366, right over onto the western limb there. Although we do have a few other little spots. Well, when I say little, they're quite big actually. But yeah. And as you can see over on the far right, no major corona holes, although there is a little bit down in the southern part of the disk there. So we'll see how that develops over the next week or so. Okay, and this is the gallery. Don't blink, you'll miss it. We've got one image from Michael down in Australia of 47 Tucanae. This was done in November.
Oh wow,
that's nice.
Oh,
lovely! Isn't that beautiful?
Wow.
you can't see that from the northern hemisphere, can you?
Definitely not.
No,
Absolutely no chance.
No. Isn't it glorious though? Beautiful.
Yeah,
Wow.
it's one of the more famous larger clusters that are visible down beyond.
Yeah.
And the other image in the gallery is one of mine, I'm afraid. Just a picture of the sun when it came out briefly during last Wednesday, I believe. And this was what it was like when we had AR 4366 almost in the middle of the disk there. And you'll probably notice down on the bottom there at about 4 o'clock position and the 8 o'clock position, all the prominence action coming along there. But it does give you an idea of how active AR 4366 was as it sped across, causing quite a few X-class flares and all the rest of it. So I was glad I managed to briefly get it.
Yeah, absolutely.
Well done.
For our viewers who don't do solar observing, it is a bit of a challenge, I think, to get both the surface detail on the left as well as the prominences off the edge. I think you have to do a little work there. Is that right, Roger?
I've got a very special technique to be able to bring out the prominences as well with the calcium filter. Normally, people usually process it so you've got a black background, but using a special curve, you can brighten up the outline of the disk, and then you can actually start to see the prominences coming up quite nicely. But it depends on how big and active those prominences are to be able to get that detail. But it turned out quite well with this actual day.
Well done indeed. Well done indeed. Excellent.
And that's what we have for the gallery.
Thank you, Roger. You want to go straight into the Constellation of the Week?
Okay.
Right, okay. So I'm going to go to Constellation of the Week now. And what we've got, Draco, or Draco, however you pronounce it.
Yes, Draco as in Malfoy in Harry Potter.
Yeah.
Okay.
Dragon.
Yeah, so dragon. Right. Okay, so it's quite a large constellation, so which is why I'm doing it and not Michael.
Thank you,
A
Roger.
few basic facts here. It's the 8th largest across 1,083 square degrees. You can see it sort of goes around quite a part around a bit of the sky, and above Ursa Major, and then above Bootes, Hercules, Cygnus, and over towards Cepheus. So quite an conglomeration of stars. So we start to find out here. You can see this is roughly how it is actually at 10 to dusk. And as you can see, almost going vertical to major. But as you can see, we've got Draco promenade almost led down there.
It is a large one.
It is, yes. Okay, so there's roughly a star curve of 70 degrees across the sky. There's a distinctive 4-star asterism which forms the head. And the Arabic nomads called these stars the protecting mother camels. Well, there we go. And this is the pronunciation going all funny. So we've got Gamma Draconis, which is Eltanen, Beta Draconis, which is Rastaban, Beta Draconis is Athabine, and Alpha Draconis as Thuban. So people might know Alpha Draconis, Thuban more than the other names of the constellation.
I mean, I presume. Well, they're all Arabic names.
They are all Arabic, yes.
And that's another constellation where the Alpha star is not the brightest.
Ah.
Yes. So Gamma is magnitude 2.2, Beta is 2.8, Eta is 2.7, and Alpha is 3.7.
Yes.
But 5,000 years ago, when we were still walking towards Jupiter, it was the North Star.
Oh,
There we go.
there we go.
There we are. So we do have a few interesting objects in the constellation. We've got the Cat's Eye Nebula.
Oh, yeah,
It's one of the brightest planetary nebula. We've got the Spindle Galaxy, which is a very good edge-on lenticular galaxy, which is also A102. And then we've got the Tadpole Galaxy, as opposed to the Tadpole Nebula, which we had from Tom, or otherwise known as Wilhelmina. And as you can see, it's got quite a long tail, so to speak, as the Tadpole Galaxy there. So obviously details, has come out, stretched out from other contacts, and
Other tadpoles are available.
yes. But we also have a meteor shower named after the Draconids, which is around the early part of October, and originates from comet 21P Giacopini Zinner.
Oh, yes.
So there we go. So,
Yes.
keep an eye out for that. So we go on to the mythology and legacy. So it's been a 100-head dragon. So it's been called. And it was killed by Hercules in his legendary 12 labors. Right, okay. And Hera placed Ladon amongst the stars near the North Pole to celebrate it. So he was, the battle was Athena drew dragon out into the sky after a fierce battle with the Titans. And Thuban was, as we heard before, 5,000 years ago, the pole star, which was interesting. And no doubt that will change again, as we all know, with the shifting. So in other cultures, we've had the Chaldeans, the Romans, and the Hindus. They also saw a dragon. The Persians were thought it was a fearsome man-eating serpent, and the Arabs also thought of it as the head of the great serpent with the star Eltanan there. And we've also got 1.5 million years ago, Eltanan passed close to the solar system, shining as bright as Sirius. There we are.
Wow.
So that would have been a quick walk over to view it.
Absolutely.
And, so in 20,346 AD, which was a Friday, the procession was over towards that star as well. So we'll be getting to that. And just as a matter of information, we've got 2 World War US Navy ships named after the Draco stars, the Etamin and the Grunim.
Oh, nice.
Oh, wow.
And it also belongs to the Ursa Major family of constellations. And there are 9 stars in the constellation of Draco that have got known exoplanets orbiting.
Fantastic.
Well. So there we go.
Thank
and
you
that's
very
all
much.
to know for Draco.
There we are. Thank you very much, Roger. So we'll be back with another constellation, a small constellation of the week next week. So there we are. Speaking of Michael, you wanted to mention something, I believe.
I did. Can you just share my screen? I'll
go on then.
Where's what I want? That's the one.
By the way, we do apologise for the clicking on the sound during that.
Right.
It's Roger's fault. It's all Roger's fault.
Yeah.
So we will try and get that resolved.
Right, I'd like to tell you about the 2026 Federation of Astronomical Societies Convention to be held on Saturday the 27th of June at Cardiff University. We have, so far we have 3 speakers confirmed. Professor Paul Rauch, using astronomy to engage students in STEM. Professor Mike Lockwood, space junk and the danger of orbital collisions, and Professor Mike Edmonds talking about the Antikythera mechanism. I can never say that. This will be a chargeable event, just £10 per person. So it's quite reasonable cost for that. So it's an all-day event on the Cardiff University campus. The ticket sales are available to Federation of Astronomical Society affiliated societies until April. Then they will be open to the general public. So if you're a member of a local astronomical society, you should be able to get the tickets shortly. And the tickets will be available through the FAS website.
Okay. Thank you very much.
Yeah.
Okay. Thank you very much for that. Always a good day, the FAS convention. Always very interesting. So if you are a member of an astronomical society.
I'm planning to be there.
Right. You may not want to go this year, viewers. Michael's going to be there, so perhaps you might want to give it a miss. So anyway. So there we are. All right, then. I believe that's it for this evening. So we would like to thank you all very much for being here, as always. Thank you for your donations. Thank you, JR. Thank you, Deep Rita, very much indeed. We will be back, of course, next week at the same time with more Space Oddities. So until then, we'd just like to say thank you for being here. Have a fantastic week. I hope the rain leaves off and that you can finally get some astronomy done, especially as the spring galaxies are coming up now. So it will be Messier time again very soon. So stay safe in the UK, stay dry if you can, and it can be very dangerous. Only 2 days ago, my brother-in-law in Wales, where it's been raining since 89 BC, went out outside to get something out of the car at night and slipped over, and his leg went the wrong way. And he's you've got some muscles down the front of your leg to your knee, which sort of control the bottom half of your leg, and he's managed to detach all of those from his knee. So he's in hospital awaiting a scan. So again, that could be in 2000 AD. All the best to my brother-in-law Dean. Not that he's watching, but he's. They've told him it could take a year before he's fully recovered.
Oh
so
my goodness!
he's got to have an operation, and then he's got to have physio. He's been a splint for 4 months, then physio, and then learning to walk again. So poor guy. But this is what happens with rain. So stay safe, everybody. Be very careful when it's slippery. And thank you for being here. And from all of us at Space Oddities, have a great week. Take care of each other. We'll see you again next week with even more stuff. So goodbye from all of us at Space Oddities. Have a great week. Bye.